Welcome everybody. My name is Hugh Simpson-Wells from Oxford Computer Training, and we're going to try and start on time. We've got a few stragglers still joining. Thank you very much, all of you that have joined. I'm here today with Rafal Lukawiecki from Project Botticelli. Rafal goes back a long way with Oxford Computer Training, and we have got together recently again to offer Project Botticelli's practical machine learning courses. And Rafal and I actually met a few months ago to discuss how machine learning relates to OCT's area of expertise, that is identity and security. And as you can see here on the slide, we did a video at that time of us discussing it. And if we could put up the first poll, I would just like to see who's already watched that video. Many of you may have done so. And if you could just let us know whether you've seen that video or not, that'd be very helpful. And I am not seeing, oh, here we go. Okay, so actually most of you haven't, and that's absolutely fine. So back to the slide, yeah. And you know, if you want to watch it, we will leave that link up at the end if you'd like to watch it afterwards. But Rafal's going to summarize in any case what he said and add a little detail to some of the points we were discussing. And then at the end, and perhaps during, we'll get some Q&A going. As with all of these webinars, it's difficult to have you all talking, so you'll have to post your questions in the chat window as text questions, and we'll either deal with them as we go along, or depending on how it's going and the nature of the question, we will deal with them at the end and hopefully have a lively QA session. So right now I'll hand over to Rafal, who will take you through his agenda and talk a little about this subject.
Thank you very much, Hugh, and welcome everybody. Thank you very much for joining us for this short webinar. I have worked in the area of machine learning, advanced analytics, data mining, and what is now called data science, pretty much for about 14, 15 years. Certainly in a productive capacity for well over the decade. But before that, my previous profession was security and data protection in particular. And I worked in that area actually when I worked with Oxford Computer Group many years ago. My connection to Hugh and his company goes well over 20 years back. What I would like to do today for you is to give you a little bit of a hint on how those two areas intersect. And for that reason, on the agenda, I would like to start with the opportunity that I think is ripe for being used now in a way it hasn't been when we hoped to apply it well over a decade ago. There are a few requirements for you to be able to do it, which I will outline after that. And really the gist of the webinar is to give you an idea of how you could use machine learning for security applications. I will share with you two of the most common approaches. Before we finish, I will highlight briefly the issue of false positives, which is something that plagues machine learning in general, is in no way unique to security, but it causes some significant issues when you use machine learning for security purposes, in particular of an ethical and sometimes seriously legal nature. And we will finish with a little look into the future, and I'll briefly talk about this concept of AI for security, which is still quite new and not many people or companies talk about it. So let's get started with the intersection of machine learning and security as an opportunity. I think it's quite significant. I think we have a chance to deliver better security, more proactive security, by relying on the knowledge that is currently hidden or hiding in underused data. I meet a lot of IT professionals when I work on projects, when I teach courses, when I speak at conferences, a lot of IT professionals who invariably come with the same idea. They come up with the rather obvious idea that we have so much data in our logs that surely there should be a way of using them to gain some insight, to do security in a better way, or at least to avoid the mistakes we are making today. And invariably, I find that it is very difficult to do it well, mainly for reasons of data quality rather than for reasons of any problems with machine learning today. But as the technology for data preparation has improved, as the machine learning technologies have improved, and above all, as they became cheaper and more accessible, perhaps now is the time to start looking at that intersection more seriously. The reasons of cost and the reasons of difficulty were the main reasons why this intersection, that is, using machine learning for security applications, has been so rarely implemented by smaller and mid-sized companies. When you are the size of Microsoft or Google, etc., of course, that area is in use. And there are many good reasons why larger companies want to apply it, which are not only to do with costs and perhaps economies of scale, but also more to do with the fact that it is very difficult for them to provide security when working with billions of devices, users, and so on, other than by using machine learning. When you don't have so many subjects or security credentials to worry about or devices to protect in a smaller or a mid-sized company, a more traditional approach based on rules and policies and man-made structures which somebody understands is, generally speaking, quite the appropriate thing to do. But as we grow, and as we want to do more with less, there is definitely an opportunity to apply machine learning even for the smaller companies. As I mentioned, this is not new. I remember talking about this as an idea at a Microsoft TechEd conference back in the late 90s. Can't remember whether it was late 90s or the very early noughts, but I outlined an idea of a system that would have used machine learning, which was at that time known better as data mining, for the purpose of building a more secure system. But that was definitely ahead of its time, not just because technology was weak, but primarily because we had significant issues with data and its quality. Let's talk about the requirements. I've already mentioned that good data is necessary. Good data is difficult to pin down, but it's easy to know when you have bad data. When you have good data, not only it's easy to build a machine learning model which validates, works, but also one that generalizes well to day-to-day applications. When you have bad data, you may be able to build a machine learning model that you can validate in your lab, so to speak, on your development machine. But as soon as you put it into real-world use, it doesn't seem to work so well. A classical example of that is when you build some kind of a fraud detection system, and it's very good at finding fraud that has been known to you before you've built the system, but is incapable of looking for new patterns of fraud. This is such a common issue that very often people give up on the goal of building a more generalized fraud detection system, and they keep rebuilding one that works often enough, sometimes almost as often as every week or every few days, just to keep it ticking over, even though this misses the point of true machine learning. In other words, building systems which understand the essence of what they are looking for, in this case, let's say fraud, and are capable of generalizing themselves to types of fraud that has not been encountered before. When I'm asked to give a high-level idea of what makes good data, I don't think anybody gets surprised when I answer that having clean data helps. Clean means not having errors, not having too many duplicates, not having obviously easy to spot inaccuracies. But from machine learning perspective, that's not enough. A much harder goal to accomplish, which is a requirement, is to have a complete and consistently aggregated data source. Complete means that not only we want to have, for example, a log of security breaches, but we also want to have a log of when things went right, when there were no issues. Having that background data, so to speak, in other words, something that shows you when the system is operating well and without issues, against which we can analyze the problematic behaviors, is essential to building a machine learning model. It is very, very difficult to use machine learning when all you have is the examples of something that's bad. Equally, it is not easy to build an ML model when you have complete data, but you are not quite sure which of those events are good and which are bad. So labeling the data with an unambiguous perhaps column which says this was a good thing and that was a bad thing is important and also difficult and sometimes requires a fair amount of manual work. Another issue arises when the data comes from multiple sources, when it is aggregated in an inconsistent manner. For example, one log contains more background data than another one. In other words, one log has a higher proportion of the good events to the bad events, and another log, for reasons of poorly set parameters or whatever else may have caused it, the other log has far fewer of the good events, but let's say it has the same number of the security breaches. Having such unevenness across the different sources of the data leads to an inconsistently aggregated data source, and that leads to a poor machine learning model, which, rather than telling you what causes the bad things to happen, will simply tell you that a cause of a bad thing happening is a particular source system from which you just happen to have a higher proportion of the bad events to the good events. Machine learning is actually quite dumb. You could almost summarize everything it does by saying that it is a frequency counting machine with some interesting statistical and algorithmic strength behind it. Assuming that you have good data, the next big thing to have is a clear goal, a simple goal at the beginning of a project. Looking for maybe even trivial examples of applications here is a great place to start. So for example, you might want to build a system that looks for clusters and patterns of your most typical security breaches, finding out what causes audit event storms, where you suddenly have dozens or hundreds of seemingly related events saying that something is bad, and that leads perhaps to performance issues or other difficulties. Spotting situations that lead to a password reset loop, where a population in your organization, not just an individual, but a group of users, seem to suddenly get stuck into resetting their passwords and apps and requesting credentials and so on. On the slightly more malicious side of things, perhaps looking for situations where an account is being changed repeatedly, maybe some email addresses or other attributes of the account are suddenly being switched around whilst audit events are rolling. Any cluster of access denials. Or perhaps you could look on the cost side and see whether there is a connection between security issues, as you can see in your logs, and subsequent expensive or time-consuming help desk calls from the same individual. These are just a few examples of fairly simple things. In general, most of the value you will derive from applying machine learning, and not just for security, is probably when you start looking for things which are a little harder to find, things which are a little bit more valuable. But that is not to say that looking for the simpler goals is of no value, because if you can prevent these relatively easy and on their own, maybe low-risk security issues more cheaply, in a more consistent way, that is very valuable too. One of the biggest values of using machine learning in any domain is that you can do things with it quite inexpensively because the technology replaces very often the need for human intervention. And there are an awful lot of things within the security environment where we certainly can reduce costs by applying it. So I would not necessarily say that a clear, simple initial goal in itself is just something that you should start with and move on swiftly onto more advanced goals. I think there is quite a lot of mileage of focusing on those simpler projects at the beginning. Needless to say, having some understanding of practical machine learning and the toolkit is also a requirement. And this is, in some ways, a domain where traditional security expertise, IT professionals, perhaps expertise, has not been so strong. People who specialize in machine learning or maybe even artificial intelligence or data science tend to be more analytically minded, and they tend to work on maybe business intelligence projects, planning, and so on. This is another area of opportunity. Maybe some of you attending the webinar are in that role. Perhaps you know somebody who is in that role, who are currently thinking of expanding your portfolio of skills. You have an IT role or an IT skill, maybe you have a security skill. Adding machine learning to it would be definitely of interest from the perspective of building up your career if you have time for it. I'm pretty certain that there will be a growing demand for IT security experts who also know machine learning. In any case, let's say that the requirements have been fulfilled. You have good data, you have defined your goal, and you have some knowledge of how to do it. How does it work? I would like to give you two ways of using machine learning for security purposes. The first one uses the so-called supervised approach, and on the next slide, I will explain the unsupervised approach. They are both valuable. Neither of them is better or worse. Before I go any further, though, with those two approaches, I would like to ask a question to my attendees. How many of you at this point are using machine learning in your organization? If I could ask Jane to put the second poll up, that would give me an understanding of what to talk about. That's quite interesting because it looks at the moment like a majority of you, if you all have pressed the button, are not using. I'm seeing 80% of you not using, 83% of you not using machine learning in your organization and 17% using. Let me change the question a little bit and perhaps let me ask you about your own personal role and experience. This is the third and the very last poll I would like you to click on, which is really whether you are personally involved or about to be involved in a machine learning project. Interesting. So it looks like slightly less than half of you haven't plans. The rest have plans. Again, half of those are about to have already started, and 2/3 of the rest about to start one. Well, this is very helpful. This is very useful. That gives me an idea that for most of you, perhaps this terminology of supervised versus unsupervised learning is somewhat new. Let me not over-theorize about the meaning of supervised versus unsupervised, because that's not necessarily very helpful. Let me explain it in a practical way. Supervised machine learning, in general, is the kind of machine learning where you teach the machine, or as some people prefer to say, you teach the algorithm, using examples of data where you can tell it what the outcome was, so it can draw its own parallels, conclusions, or correlations between what it sees and the outcomes that you are trying to teach it about. In practical terms, it means that you need to define your goals, security goals in this case, in terms of data. And in practical terms, that means that your data is almost always structured as a flat table, very often with a lot of columns. Those tables easily can have hundreds of columns. Some situations which use unstructured data will easily go into hundreds of thousands of columns, but let's not talk about those examples for now. Let's just focus on the more typical situations where you will have dozens or hundreds of columns. Those columns describe whatever is legally and ethically analyzable as an attribute of a security event, of a person, a resource, a credential, an application, interface, pretty much anything that you decided to study. So those could be pre-processed log events. A log event is an event, or it could be some summary characteristics of a user account, or perhaps those could be attributes of an application aggregated at some point in time, where various columns could denote the number of security issues that you have been dealing with. There's an infinite way in which you can prepare the data for machine learning. But let's say that you've got your one row per case and you have your columns which describe those analyzable attributes. And what makes this supervised learning is that you now have exactly one column, no more, exactly one column, which is also known as the label column, which represents the security outcome that we want to model. That security outcome, especially in your early projects, should be a Boolean, something that is true, false, or if not a Boolean, then anything that is true valued, something that is like a threat or benign, denied or granted, problematic, okay, risky or safe. It does mean that you have to simplify your data a good bit, and the process of simplifying your data in itself is a big part of how you start a project. Very often starting the project requires spending inordinate amount of time preparing your data into this format, and there is no way to escape that. This is just the way it is. Good. So you have your data. There is that one column which says that this row represents an event which was anomalous, or this row represents a security threat. And then you have lots and lots of other columns which describe what this event was, where it happened, at what time. Maybe even you link to previous and related events. So the width of that table can be tremendous if you end up putting multiple event log entries into one row of data. Let's say you've done it. Now comes the time to train a model using your chosen machine learning algorithm. Maybe you will be using a decision tree, which is a very powerful algorithm that I use extensively. Maybe you will use logistic regression. Perhaps you will even risk something like a neural network. I say risk because the problem with neural networks is that what you build may work very well, but it's very difficult to understand why it works and how to explain it. In either case, whether it's decision tree, logistic regression, or maybe that neural network, you have just built what we call a classifier. It is a classification model. It is capable of classifying previously unseen events as being a threat or not. And this is how you would use the supervised approach. First, you build and validate that model using the data based on historical events. And now you have a machine which is capable of predicting whether what is happening right now is a threat or not. You feed it effectively a set of attributes describing the currently undergoing action, event, operation, connection, person logging on, and so on. And it spits out a number, which is a probability that this is a threat that you need to take care of. This means you can use it live. But you can also use it after the fact to do a historical analysis of events that just took place or perhaps took place last night to fish out some suspicious or risky events for further examination. So this is one of two ways how you can use machine learning for the purposes of security. The other approach is called unsupervised. And just like with supervised, I don't want to explain too much theory of it, but from a practical perspective, the biggest difference is that even though you prepare your data just like for the supervised approach, you will not have that one column that's the target, also known as the label, that tells you whether an event was or was not a security breach. In other words, what you have now is still rows of data that could be events from a log, accesses, or perhaps some security credential issuance entries, or whatever it is that you decided you wanted to analyze, accounts, devices, sensor readings, and so on. But you do not say specifically that one of them is bad and another of them is good. In fact, what you are going to do is you are going to use machine learning algorithms such as clustering, such as association rules, those are two of the most frequently used at this point, to find the natural groupings or natural connections between cases. So what happens this time is the algorithm will tell you that some of your events are similar to other events, or it will show you paths, how certain events often occur with other events. And depending on the algorithm you have selected, it may even show you what leads to what. So you might have simple association that says that two things happen together, but you don't know which one comes first. Or you can build a model which tells you when this happens, then that happens, and after that, something else happens. Well, this is very interesting for many reasons. First of all, it will show you typically a few clusters that will contain a lot of cases. You will have majority of your events, of your security credentials, of your accounts, and so on, grouped into a relatively small number of very large clusters. However, and that's where it's really interesting, you will also find a few very small clusters. By small, I mean clusters that do not contain a lot of cases, that will contain things which are rare. And those rare things require or warrant further analysis. Very often, those smaller clusters are not threats, they are not problems, they are just unusual behaviors. In which case it's interesting to know why they are unusual and whether you even should worry about them or not, or do anything about them or not. Very often they are perfectly benign, rare groupings of events or cases. However, if this all works out well, you will also find a small cluster, which is usually one of the smallest, of something that you really do not want to see happen in your environment. And this is really the Sherlock Holmes, so to speak, use of machine learning, because it looks at your data in an unsupervised manner, meaning you are not guiding it, you are not telling it to look for good, bad, threats, etc. But it does find for you little groupings of things that occasionally turn out to be worrisome. This approach can also be used together with a supervised approach. So you can have a situation where you do a bit of both. The very typical way to do it is to start in an unsupervised way, to learn more about your data, learn more about the events, identify threats this way, and then having marked those events as threatening or not, build a supervised system from them, which you subsequently use for predicting the probability that something happening is a risk or a threat. And there are many, many other ways how those things could be interacting with each other. For example, you could create a diagram that shows connections, that shows you that this type of event is related to another and related to another. And then somebody says, oh, well, how about we focus on a particular behavior that we are finding worrying? Well, you may want to use this associative analysis to tell you what leads to that worrying behavior and actually look for causes of it. In many ways, both of the approaches are a mainstay of applying machine learning for any purposes we use it for, and I'm sure that they would be both useful for a security application. Unless, of course, it leads to problems. And the number one issue that you need to solve somehow, which is not unique to security, but it really plagues any machine learning application, is the issue of false positives. A false positive, from a security perspective, means a detection of a threat that really is not a threat at all. That's something benign. For example, raising an alarm when somebody goes through a metal detector at an airport and that person has no metal on them. This is actually in itself an interesting question to ask. What does a metal detector really do at an airport? But we don't have time to go into that because that's surprisingly complex and slightly perhaps even political in nature. But to cut a long story short, we all accept the fact that we will be pulled over for unnecessary pat downs and stress and delays because we accept the fact that without having some false positives, that system would not work at all. And exactly the same applies to machine learning. You will have false positives, and you need to figure out how to deal with them. The first way how you can deal with those false positives is to tune your model to minimize them. This is a great approach because the fewer false positives you have, the less annoyance. But there is unfortunately a major compromise that you have to strike. As you tune your model to reduce the false positives, every machine learning model in existence will also, unfortunately, increase the number of false negatives. False negatives are threats you missed, the situations you should have identified as a problem, but you haven't. And the easiest way to get rid of false positives altogether, which unfortunately will also increase the number of false negatives unacceptably, is to switch off the system. If you switch off the metal detector at the airport, it never beeps. You'll never have a false positive, but unfortunately, you miss out all the people carrying whatever it is you want to detect, and the number of false negatives grows to an unacceptable level. Finding that compromise between false positives and false negatives is a business decision. And by business here, I mean the business of security. So it is a decision between people who have something to lose and people who will be inconvenienced by your security. And security is always an inconvenience. So this is a very delicate balance that you need to strike. But there is another side to dealing with false positives, which is even more important than tuning the model correctly. Having a clear procedure how to act on a positive detection, in other words, understanding that a positive detection can be a false one and dealing with it in a way that's just, that is ethical, moral, and legal, is even more important than balancing and tuning the system. And this is particularly important when we are considering fully automating your security responses. And this is an area that makes me a little bit uneasy because I am increasingly seeing situations where security or fraud detection systems do not deal with false positives in a way that is just, in many cases, even ethical, not to mention legal. Classically, this is how it goes. When a company is small or mid-sized, they will isolate the action from a machine learning system. In other words, the ML system says, this looks like fraud, do something about it, and a human being intervenes, looks at that and says, I don't think so, and the person is not inconvenienced. Or the machine learning says, this looks like fraud, do something about it. The person looks at it and says, oh, indeed, perhaps we need to do something about it. And a human action follows, which affords the subject of this inquiry due respect, care, ethics, and so on. That's fine. This is a good way to do it. I have customers, especially in the insurance industry in some Nordic countries, who rely on this approach quite extensively, and I like it very, very much. But there is a worrying trend of acting on something that comes from a machine learning system automatically without having a person in the middle. And this is where the large organizations unfortunately do it, because it's expensive for them to dispatch a human being to every situation that is highlighted by some machinery. And this is where it causes issues. First of all, it is not just. It means that otherwise benign, unsuspecting individuals are inconvenienced, denied a service, perhaps even tarred with some unpleasantness because a computer thinks that there's something wrong with them. And it gets worse. It can get as bad as denying something that legally shouldn't be denied to the person. In some countries, for example, in China, systems of this nature are used almost in a brutal way. For example, to deny people ability to travel by train. At the last Chinese New Year, more than 8 million people were denied the right to travel by train because of a machine learning model detecting that their so-called social score wasn't high enough to be trustworthy. Now, without politicizing this webinar any further, let's say that there are perhaps different reasons why that country has done it that way, which are not only to do with machine learning, but the risk is very significant. And this is why the last thing that I wanted to talk about in this webinar, security artificial intelligence, follows this discussion about dealing with false positives. Well, first of all, let me excite you, hopefully, with this vision. The vision is that we have a system, whatever it is, could be a line of business application, could be a website or some commercial system. We have a system that self-monitors its own behavior by effectively building or rebuilding or updating an existing machine learned model. So you've built a machine learned model from the data that you prepared using the suggestions I shared with you earlier, and you validated it and you tested it and it all looks good. Well, this system can raise alarms based on predictions rather than rules. So unlike in a classical world where you have to write rules and policies that decide what is and what is not possible or allowable, this system can raise an alarm simply because it predicts that the probability of an event happening right now is so high that it warrants being an alarm. In fact, you can go one step further and you can make that system automatically prevent access. So the system can say, oh, I am afraid that what is happening here is problematic. I will stop this action from happening. This gets very interesting because the action of the system could have been a valid or an invalid one. And if that's all, if we basically left it at this, system makes good or bad decisions and that's it, it would not be artificially intelligent. But here comes the opportunity that we can close the loop, so to speak. As long as we can feed the system back information, whether its action was valid or invalid, we can reinforce its own learning process. Hence, in machine learning terms, we talk about reinforcement learning, so that it improves itself from its own actions, provided we close that loop, provided that the model is updated on a regular basis, and most importantly, provided that it is continually validated. In other words, we continually apply tests which are very well understood and common in the world of machine learning to make sure that the model, that the system is still statistically valid. This will create what, by any definition used today of artificial intelligence, is artificially intelligent. Because the system changes its own behavior based on what it observes, based on its actions, and based on its goal to increase the security and safety of your application. Whilst this is quite exciting, let me stress that it is still very rare today, and perhaps that's a good thing. I talked about a system like that in the 90s, and even though I was more enthusiastic about it at that time, I'm rather glad that those systems did not get implemented as widely then, and they are not yet being implemented as widely today. The main reason why is because we have that issue of not being able to deal with false positives well. Closing the loop from this was a bad action, you shouldn't have denied this person access, and making the system learn from it means we need to know that an action was wrong. But in many cases, when you automatically act on something that is a false positive, the person will go away. They will do whatever they want to do in a different way. So you will not be able to know that you made the wrong decision. That's a very difficult problem to solve. And secondly, perhaps a good reason why we don't want these systems to be in place too early is that we need to be able to trust them. We need to trust such autonomy. We need to be able to trust that something can be almost an automated policeman before we can apply them in the real world. Having said that, I'm seeing companies implement these solutions slowly and internally, and I am sure that they will happen in the future. And I hope that at least some of you listening today, and perhaps those of you who might be watching a recording of this webinar, will bear in mind the issues, limitations, and concerns that we have that need to be addressed before deploying such systems in production. And pretty much with that thought, I am coming to the end of my presentation. I will let Hugh say a few words in a moment, but this is also a good time for those of you who have a question that you would like to discuss or answer, to type your question into a window that is somewhere on your screen in the control panel, and I will be delighted to answer any questions that the time allows, and we certainly have a good few minutes left. And to those of you who joined midway, if you missed the beginning, our video in which we discuss some other aspects of machine learning and security, including biometrics, passportless travel, and so on, ocg.tech/mlvid is the short link to that video. And needless to say, I would be delighted to meet you at one of my practical machine learning courses, holding 3 of those before the end of the year. The one that I'm doing together with my friends at Oxford Computer Training in UK, 25th to 29th of November. You can sign up using that link, and if you are interested in attending it outside of UK, or you don't want to travel to UK, have a look at projectbotticelli.com/courses for my other locations. Right, so I'll wait for any questions, and in the meantime, off to you, Hugh.
Well, Rafal, thank you very much for that. Actually, I've got a question, which is you stress practical machine learning as the name of your course or courses. Do you want to just say a little bit about what people can reasonably expect to take away from such a course relating to the topics that you've been talking about?
Sure. Thanks for asking. In simple terms, I prefer not to teach theory for theory's sake. I prefer to teach machine learning the way you would use it in reality. I find that there's a lot of training available online, both free of charge and for some money to be paid, that focuses on algorithms for algorithm's sake, on the wonderful theory behind it, and algebra and science, which is fascinating and riveting. But when somebody comes to doing a project, they kind of stare at a screen of a computer that has everything installed, and the first question is, what do I do now? Where do I begin? And that's the main thing that I deliver in my courses. I teach people, one of the first things we learn is how do you convert your business need into something that you can implement as a machine learning project. And of course, in the process of doing that, I also teach you about the algorithms, about data preparation, and above all, the key subject of the course is validation, making sure that whatever you build, however you build it, works and is trustworthy and can be deployed to production.
Okay, thanks very much. Well, that's great. Thank you very much, Raf. We don't actually have any other questions, so either everybody was asleep, or more likely you covered in great detail the topics that you said you'd cover. Unless anybody has got a question they want to post at the last minute, we'll draw this to a close and say thank you very much, and we will send links out to everybody to the video, well, to all the relevant links.
Thank you very much, everyone. Thank you, Hugh.
That's it. All right. Bye-bye, everybody.